In this video, we will learn about chemical shifts in NMR and what are the structural factors in molecules that influence the chemical shifts that certain nuclei will show up at in the data. So it turns out that the frequency at which a nucleus absorbs radio energy depends on a few different things. So the first major issue is, well, what is the element that you're looking at? So for each element, it's going to show up at a very different frequency range. So for example, a 400 megahertz instrument that looks at protons will need to go down to 100 megahertz to look at carbons. The second factor is, well, what are the local magnetic fields that are generated by electrons near to the nucleus? So the second factor is that electrons actually generate their own local magnetic fields in the presence of this external magnetic field, and these local fields will either be aligned with the external field, causing the nucleus to see a larger overall magnetic field, or these local fields will be aligned against the external magnetic field, causing the nuclei to perceive a smaller overall magnetic field. There's two ways to generate these local magnetic fields. The first is just that each electron will contribute some amount of this local magnetic field. So we think about this in terms of just electron density. The more electrons there are, the more they just shield. It turns out that in the presence of an external field, electrons will generate a local magnetic field that opposes the big one. So electron density, the more of it there is, the more shielding there is of nuclei from the external field. However, there are also certain arrangements of electrons and bonds that produce a non-uniform magnetic field that's different from the one here in part A. In this non-uniform version, this is called magnetic anisotropy, and that can both shield and de-shield various nuclei. So I'm going to pull up two sets of data here. So the left here is the proton NMR for this molecule ethyl acetate, and then on the right is the carbon NMR for a molecule of hexane. So if you're looking at this and you look very closely, you'll see that both x-axes are presented in the same units. They're both presented to you in ppm units. The confusing part about this is that this makes you think that what we're looking at on the left here is a 0 to 10 subset of what's on the right here, which goes from 0 to 200. That's not the case. What we have to remember is that this ppm is relative to the megahertz of the element. So for hydrogens, these are parts per million deviations from 400 megahertz, let's say. The carbon NMR now, these are parts per million deviations from 100 megahertz, or whatever megahertz the instrument is running at for carbon. When we're talking about chemical shifts, there's a little bit of terminology that we want to try to get used to. So these are shown here in red and blue. And what the terminology is trying to do is to relate everything to a relative either shielding or de-shielding. So if we're closer to 0, that means the nucleus is shielded relatively, and if we're further away from 0 in a more positive direction, then the nucleus is less shielded or de-shielded. Kind of in the same way, the further left we are on this scale, the more downfield we are, because the field of the NMR has gone down, whereas the more right we are, the higher the field is, and that's why we're called upfield. So of course within the relevant regions of proton NMR and carbon NMR, there are areas that we can define ranges for common types of carbons and hydrogens. So let's look at carbon first. Generally what we'll see is that carbon NMR goes from 0 to 200 ppm. It can go larger than that and it can go more negative than that, but the normal range of values is here. The general types of carbons that we'll look for are carbonyls, so carbon double bonds to oxygen. That shows up in this 150 to 200 plus ppm region. Carbon-carbon double bonds tend to be more like 100 to 150. Carbon-carbon triple bonds are more like 50 to 100. Carbons bonded to heteroatoms, so just non-carbon or hydrogen atoms, those tend to show up also in this 50 to 100 region, maybe a little bit less. And then finally, carbon single bond to other carbons, those tend to show up around 0 to 50. This pattern is not too different in proton NMR. So for example, if we look at the carbon-carbon double bond here, that's in kind of the middle of the generic range for proton NMR, which is 0 to 12-ish ppm. The hydrogens that are attached to a carbon that is attached to a heteroatom, those tend to show up in this kind of a 2 to 5 region right here. The hydrogen on sp carbon, that's going to be around 2 ppm. And that's similar and overlapped with hydrogens that are just attached to carbons attached to other carbons. On the more downfield side of the proton NMR range, we see this is the aldehyde proton here. That shows up very downfield, and carboxylic acids show up even more downfield. So those are very general ranges. There's all sorts of tables with more detailed information and kind of separation of these ranges into even smaller ranges. But we will want to be able to compare two situations and determine which nucleus might be more upfield or which one might be more downfield. So naturally there are a lot of different factors to consider, and so we'll go through those now. So the first effect to consider is that of resonance. So if electron density of electrons around nuclei can impact chemical shift because of shielding and deshielding, then naturally resonance forms will be very important for telling us whether or not there is more or less electron density around a carbon or hydrogen or whatever other element than we normally expect. So to give you an example of that, so we can compare these two molecules, so cyclohexene versus cyclohexenone, where we have the carbon-carbon double bond in both cases, but because of the carbonyl here, we're introducing a little bit of resonance. So if we look at just the cyclohexene, we'll find that the two sp2 carbons will have a chemical shift of about 127 ppm. If we look at the cyclohexenone, those carbons will have differing chemical shifts now. So what I'm trying to do is to draw the comparison that this carbon is that one, let's say, and just compare those two across here. So by putting in the carbonyl here, we've caused the red carbon to not change very much, so that's about the same. However, the blue carbon has shifted downfield, so a larger ppm. It is deshielded significantly. It goes from 127 all the way to 150 ppm. Of course, if we're looking at the ketone itself here, that ketone carbon, that has a chemical shift of 199 ppm, so very downfield. That kind of fits with what we expect from our typical ranges. So the reason for this difference in chemical shift is because of resonance. So because we have a conjugated ketone, so double bond conjugated to the ketone here, that tells us that we can draw the resonance form that looks like this right here, where we introduce some partial positive charge, or really formal positive in the resonance form, on this top carbon, which was in blue. And in the other significant resonance form, for the carbonyl itself, we can have that partial positive charge showing up on the carbon of the ketone. So these two resonance forms are responsible for reducing the amount of electron density at this carbon and at the ketone carbon, which is then observed by NMR spectroscopy in the form of these larger chemical shifts. So now let's look at the same two molecules, but in proton NMR, and see how things compare. We can look at the alkene there and look at its two hydrogens. Those will show up at 5.7-ish parts per million, which is exactly the range that's indicated up here. But if we look at the cyclohexenone, those two protons are now different. They're different because they, for me, I look at this and I notice that this hydrogen is closer to this oxygen, this hydrogen is further away, so they're going to be different. Their chemical shift is also different because they are exposed to different carbons with differing amount of partial positive charge arising from these two resonance forms. So the hydrogen attached to the carbon that has some amount of partial positive character, that's more downfield because it is deshielded. So the carbon atom's loss of electron density also impacts the hydrogen that's attached to it. Hydrogens will always feel a little bit of the deshielding or shielding that the carbon atom it's attached to feels. The hydrogen attached to this carbon doesn't change as much, changes a little bit for reasons we'll go into later, but definitely not as much because there is no resonance form that removes electron density from this carbon. The second effect that we will look for in NMR spectroscopy is called the inductive effect. And so in the inductive effect, what we're really thinking about is the electronegativity of an atom, and that the electronegativity is going to withdraw electron density from nearby neighboring atoms. So an example of that can be found in carbon NMR of pentane versus the carbon NMR of 1-fluoropentane. So if we're looking at just the pentane, what you'll find is that the central carbon will show up at 34.5 ppm, the next one over at 22.6 ppm, the last one at 13.7 ppm. So these carbons are different from each other because the central carbon is bonded to 2 hydrogens and 2 carbons. Carbon is more electronegative than hydrogen, so that means that overall this carbon experiences more neighboring carbons pulling electron density away compared to this carbon at the very end. We can compare that to fluorine, where fluorine is so electronegative it makes this difference much more obvious. And what you see is the carbon directly attached to the fluorine, that's shifted a lot. So from the default of somewhere between 13 and 35, we're going all the way to 84 ppm. The next carbon over at 30.6 ppm still feels a little bit of the electronegativity of the fluorine, but it's definitely significantly less. And then the central carbon is feeling even less than that. Same type of pattern is found in proton NMR. So if we look at now butane versus 1,4-fluorobutane, the chemical shifts follow the same trend for the carbons, where these methyl groups have a more upfield chemical shift compared to the kind of central CH2 groups. If we put a fluorine on the molecule, that changes things a lot. So the hydrogens on the carbon attached to the fluorine, so I'm thinking about the 2 hydrogens here, those have a chemical shift of now 4.34 parts per million. Again, drastic shift from 0.9. The next carbon over, its hydrogens are showing up at 1.6 ppm. That's relatively closer to where they would be in butane. And then finally, the methyl group that is multiple bonds away from the fluorine, that's showing up at almost the default value of 0.91 for a regular methyl group. This one's at 0.95 ppm. So the point of showing you all this is to show you that an electronegative atom will significantly impact the atom it's bonded to. So that's a huge inductive effect. And it will have a very minor inductive effect on the next atom over. And then even smaller than that on the next atom over, so on and so forth. So as a rule of thumb, these inductive effects are usually the most significant from 1 to 3 bonds away and have just fallen off to almost 0 beyond that. It's not non-zero, but it's just very small in the context of all the other effects in the molecule. All right, those first 2 effects on chemical shift, those dealt with electron density changes and how those electron density changes allow us to judge chemical shift. The third effect we'll talk about, magnetic anisotropy, is not dealing with the difference in electron density, but rather with the fact that the electrons that are within an external magnetic field can themselves generate other kind of second local magnetic fields that have some sort of anisotropy. The word anisotropy means that it's not uniform in all directions, so in some directions this field will be more positive or more negative. So basically, what's happening is that in the external magnetic field, electrons are circulating around in the molecule, and it turns out that that circulation will depend a bit on the external magnetic field, or B naught here. Typically we'll see this effect in pi bonds, but actually it shows up in all types of bonds. It's just most significant for pi bonds. Alright, so what happens is in an external magnetic field, when that external magnetic field is perpendicular to a pi bond. So what you're trying to imagine is that in a sample that's undergoing NMR irradiation by radio waves, a molecule might be like this, it might be like that, it might be oriented this way or that way, but at the times where it's perpendicular to the external magnetic field, the circulating electrons in the pi bonds will cause a secondary magnetic field, which we'll call B sub E. So in graphical form that looks like this. So we have the external magnetic field B naught that induces the pi cloud or pi electrons of the pi bond here to undergo circulation. So just kind of note that I'm tilting the ethylene molecule here into the plane a little bit. So we should have some circulation up here and also some circulating down here. And because of physics, and I'll leave it just at that, that then leads to secondary magnetic fields that are circulating now this way. So again, just to be clear, there is the external magnetic field causing electrons to circulate, which then causes another secondary magnetic field. So what we're looking for then is, what is the secondary magnetic field doing to the nuclei that it's impacting. Let's look at these two hydrogens out here. If you look at them, the vector of the magnetic field is, generally speaking, in the same direction as the external magnetic field. So what we think of is that this magnetic anisotropy is increasing the total magnetic field that's experienced by these hydrogens, and actually also a little bit by these carbons. The same is, of course, true on the right side here. And so what we're saying is that the alkene carbon and the vinyl hydrogen experience a larger magnetic field that is then considered a de-shielding situation because the nucleus is exposed more to the magnetic field. The anisotropy of this secondary magnetic field tells us that some parts of this field are going to experience more shielding or less of a chemical shift. And so that shows up if an atom happened to be, for whatever reason, in 3D space, located kind of above or below the plane of this molecule. The magnetic field vector in the B sub E there will be pointed the opposite of the external field. That means this would cancel out some amount of the external magnetic field. Then the blue hydrogen here would feel less external magnetic field overall, thus be a little bit more upfield in the data. These magnetic anisotropy patterns are just some that we kind of want to get used to in our mind. So generally speaking, what we'll see is that pi bonds, such as these here, will have a region above and below, so that's indicated by the minus delta here. So above and below that are more shielded, and then in the plane of the pi bond here, the atoms, the nuclei there will be relatively de-shielded. So things are different for a triple bond. Because a triple bond has kind of that cylindrical nature, the circulation, instead of going orthogonal to the pi bond here, it's going around the triple bond. And so because of that, what happens is actually the areas that are shielded are along the axis of the triple bond, and the areas that are de-shielded are now kind of above and below. You can kind of extend this thinking to aromatic rings. So aromatic rings have very strong magnetic anisotropy. So everything in the plane of the aromatic ring will be very de-shielded. Anything that happens to be located above or below the molecule will be very shielded. So those were the pi bonds. As I was alluding to earlier, though, you can actually define anisotropy for single bonds and rings. It turns out that a lot of the data tables that we look at, those already kind of factor in the impact of carbon-carbon bonds, since every single molecule has carbon-carbon. So the major one to take away from here is that in cyclopropane and cyclohexane, the real impact is that you end up almost looking like a pi bond, where you have kind of regions above and below the ring. A little bit harder to see here, but it's also the case. Regions above and below the ring that are more shielded, and then kind of along the plane of the ring, regions that are more de-shielded. Again, if you're looking at this graphic, just make sure to remember that the plus delta here is plus ppm, not positive charge. So just give you 3 examples. So the impact of anisotropy is huge. So here's a comparison of an aldehyde and an alcohol. So the only difference is that the hydrogen here is connected to a carbon that's either double bonded to oxygen or single bonded to oxygen. So this hydrogen is the same number of bonds away from an oxygen in both cases, which means that the inductive effect is the same or roughly the same in both cases. So the only difference is that magnetic anisotropy of this pi bond is de-shielding this hydrogen and causing a 6 ppm shift compared to the case where there is no double bond here to de-shield the hydrogen. So pretty significant. You can also look at this in this series here. So if we look at the kind of methyl hydrogens in this series, so if there's no anisotropy around, that is at 0.88 ppm. If you have just one pi bond here, that's at 1.73 ppm, so a little bit more downfield. And then finally, if you are for example, on a benzene ring or an aromatic ring now, you're shifted even more. And the reason for that is because now there's kind of this bond and that bond's worth of pi bonds. In this case, 1.5-ish pi bonds worth of anisotropy that is hitting these 3 hydrogens. So this one is a little bit more de-shielding than in this molecule. And finally, here in cyclohexanes, the impact is that the axial and equatorial hydrogens in a cyclohexane can actually be distinguished by NMR if the conformational changes are slow enough. So by putting two methyl groups here, I can make this cyclohexane not chair flip too much or too fast. That then causes these two hydrogens to show up differently. So again, the axial hydrogens are the ones above and below the ring. Those are more shielded, as according to this graphic over here. And the equatorial hydrogens, those are in the plane of the ring. Those are more d-shielded. Okay, two more trends for us to think about. The first of these is the heavy atom effect. This is really only relevant for elements in row 5 of the periodic table and below, and the vast majority of the time it's relevant is in the case of iodine. So the idea is that when we get to bonds between carbon and elements that are in row 5, the atomic radii are so big for these elements compared to that of carbon that essentially this radius is starting to, if we want to visualize this way, kind of creep onto the carbon itself. So instead of just the bonding electrons affecting this carbon, we're actually getting some of even the valence electrons of iodine affecting the carbon over here. And so overall, because there's more electrons around that carbon, then that's overall shielding. And if that's shielding, that leads to the upfield shift. So for benzene, the sp2 carbon's at 129 ppm, whereas in iodobenzene it's at 94 for the carbon directly attached to benzene. Now one carbon away from that, so here what you see is that the chemical shift is actually a little bit more d-shielded or downfield, and so that's because this carbon is now experiencing some of the inductive effect of iodine, but it's too far away to experience the heavy atom effect. Once you go out to here, then this carbon doesn't experience either the inductive effect or the heavy atom effect, and now its atom value more comparable to that of just benzene. Alright, the last consideration is that all of these protons that we've thought about have been attached to carbon. Protons can obviously be attached to other elements as well, so what happens in those cases? Turns out that if we're thinking about at least OH and NH types of hydrogens, those are considered exchangeable, and if they're exchangeable, that leads to unpredictable chemical shifts and much broader signals. So let me first show you what I mean by broader signals. So that would look like this here. So if we're kind of comparing the narrowness of these peaks here compared to this one right here, definitely the hydrogen there is much broader. And if you were to prepare this sample multiple times and take NMRs, you might find that this signal is at 3.9 in some cases, maybe it's at 4.2 in others, but it'll tend to shift around a little bit depending on how you prepared the sample, whereas these signals are almost going to be invariant. So the reason these hydrogens are exchangeable is because they are somewhat acidic. If we haven't talked about acid-base chemistry yet, one thing you can just really think about is that these are also hydrogen bonding hydrogens. And so you can kind of think about a process like this one, where the black molecule encounters an identical copy of itself, a blue molecule. They hydrogen bond together and exchange their hydrogens, producing these two new versions. The problem for the NMR instrument is that as it's kind of collecting data, some of the molecules are kind of in the middle of this process. So that means that the blue and the black hydrogen might not be kind of just only bonded to one oxygen, but they might be kind of partly shared between two oxygens. And if they're in a different environment, they're going to have a different chemical shift. And so what we're really capturing is that there's a range of chemical environments that this hydrogen exists in. And so that's just something to look out for. You'll see this in data tables as well, that the OH and NH are indicated as very wide ranges as potential locations. Again, that's because of the fact that they can exchange and mix and show up in different environments, even though you have just one molecule that you're analyzing. Okay, so that was a quick look at chemical shifts and the structural factors that influence chemical shifts, and also the magnetic anisotropy that can lead to changes in chemical shifts.